we just found stars that should not exist. 13 billion light-years away, the James Webb Space Telescope captured light from giants 100 times more massive than anything burning today. They formed when the universe held nothing but hydrogen and helium, pure primordial gas collapsing into furnaces, so hot their surfaces reach 90,000 degrees. We are about to witness gravity bend light itself and discover how the first explosions created every atom in your body. If you enjoy this, hit like and subscribe. Prepare yourselves. We begin. March 2024. Astronomers reviewing James Webb Space Telescope data freeze at their screens. A spectrum appears that makes no sense according to modern physics. The light comes from a galaxy called LAP-1b, so distant its photons have traveled for 13 billion years to reach us. What they see in that spectrum contradicts everything we know about how stars should behave. The emission lines show something impossible. Massive amounts of high-energy photons, far more than any known stellar population produces. The wavelengths indicate temperatures that dwarf anything in our local universe. Lead researcher Eli Visbal from the University of Toledo examines the data repeatedly. Every calculation points to the same conclusion. These are not normal stars. The spectrum reveals another anomaly. Almost zero heavy elements, no carbon signature, no oxygen lines, no ion absorption, just hydrogen and helium, the two simplest atoms in existence. Modern stars contain metals, elements forged in previous generations, but this galaxy shows virtually none. The gas appears pristine, untouched, primordial. Scientists have theorized about such objects for decades. Population, 3 stars, they called them. The first generation. Giants born from pure hydrogen and helium clouds shortly after the Big Bang. Stars so massive they would make our nearest star look like a grain of sand beside a boulder. But finding them seemed impossible. The universe has hidden them well. These objects would have lived fast and died young, burning through their fuel in just a few million years. By comparison, our star has burned steadily for 4.5 billion years and will continue for billions more. The first stars exploded as supernovae before the cosmos was even 1 billion years old, yet here sits evidence in the data. The spectral signatures match theoretical predictions made in computer simulations. High-energy photons consistent with massive stars. Low metallicity consistent with primordial formation. Mass estimates suggesting each star weighs about 100 times what our star weighs. Every piece fits. The galaxy appears frozen in time. We see it as it existed just 800 million years after the Big Bang. Back then, the universe was still an infant, barely 5% its current age. Galaxies were just beginning to take shape. The cosmic dark ages were ending. But questions multiply faster than answers. How did these monsters form from such simple ingredients? Why did they grow so large? What forces governed their birth? And most important, what happened when they died? What comes next reveals something even stranger about the telescope that found them. 1915, Albert Einstein publishes his theory of general relativity. Among its predictions, massive objects bend space-time itself. Light traveling near something incredibly heavy will curve along that warped geometry. At the time, this seems like abstract mathematics. Nobody imagines we will use this effect to peer into the universe's childhood. Einstein predicts something specific. A massive object positioned between Earth and a distant light source will act like a lens. The gravity does not pull the light. Instead, it curves the space through which light travels. Photons follow the shortest path through that curved space. To us, the path looks bent. The effect creates magnification. Light from the background object gets stretched, amplified, and sometimes duplicated into multiple images. The more massive the intervening object, the stronger the lensing. Galaxy clusters, containing thousands of galaxies worth of mass, create the most powerful natural lenses in existence. For decades, astronomers observed this gravitational lensing effect but cannot fully exploit it. Telescopes lack the sensitivity to capture extremely faint, magnified objects from the early universe. The light is simply too dim, too redshifted, too distant. Enter James Webb Space Telescope. Launched December 2021, it carries a mirror 6.5 meters across. That mirror collects infrared light with unprecedented precision. Infrared matters because the universe's expansion has stretched ancient light into longer wavelengths. What started as ultraviolet radiation from early stars now reaches us as infrared. Webb's instruments can detect photons that traveled over 13 billion years. But even Webb needs help to see the absolute faintest objects. That is where Einstein's prediction becomes crucial. Astronomers target their observations carefully. They point Webb at massive galaxy clusters known to create strong gravitational lensing. These clusters sit between Earth and the distant early universe. Their combined mass, equivalent to millions of billions of stars, warps space-time dramatically. The technique works like compound magnification. Webb's sensitivity provides the first level of zoom. The cluster's gravitational lens provides the second. Together, they reach objects that would otherwise remain forever invisible. Without this cosmic cooperation, population 3 stars would stay theoretical. The phenomenon even has a specific signature. When a lens perfectly aligns with a background object, the light forms a ring called an Einstein ring. Slight misalignments create arcs. Multiple images appear at different positions. Astronomers can measure these distortions to calculate the magnification factor. For LAP1b, that factor reaches 100. The cluster's gravity amplifies the galaxy's light by 2 orders of magnitude. Without that boost, Webb could not gather enough photons to analyze the spectrum. But which cluster provided this incredible magnification? The answer involves a cosmic collision billions of years in the making. 4.3 billion light-years from Earth. 2 massive galaxy clusters approach each other. Each contains hundreds of individual galaxies plus vast clouds of superheated gas. Dark matter, invisible but gravitationally dominant, makes up most of their mass. They have been falling toward each other for hundreds of millions of years. The collision unfolds in slow motion by human standards. Galaxies do not actually smash together like cars. Space between stars is too vast. Instead, the dark matter halos interpenetrate. Gas clouds collide and heat to millions of degrees. The X-ray glow becomes intense enough to detect across billions of light-years. This system bears the designation MAX-J 416. The Massive Cluster Survey catalogued it years ago based on its X-ray brightness. Follow-up observations revealed its unusual structure: 2 distinct cores, separated by significant distance, gradually merging. The geometry makes it exceptionally efficient at gravitational lensing. Hubble Space Telescope studied MAX-J 416 as part of the Frontier Fields program. That campaign targeted 6 galaxy clusters specifically chosen for their lensing power. Hubble captured deep images showing the cluster's structure. Hundreds of galaxies appear in the foreground. Behind them, stretched and distorted, background galaxies form long arcs. The cluster's total mass reaches approximately 1 million billion times our star's mass. Most of that mass is dark matter, detected only through its gravitational effects. The distribution of mass is not smooth. It forms 2 main concentrations corresponding to the merging clusters. This bimodal mass distribution enhances lensing efficiency. Light passing near either concentration gets bent. Light passing between them experiences complex deflection. The cluster produces 237 multiple images from 88 background sources. That represents an extraordinary lensing rate. Astronomers measure something called the Einstein radius. For MAX-J 416, that radius extends about 26 arcseconds. Within that region, the cluster's gravity is strong enough to create multiple images of background objects. The critical curve, where magnification theoretically becomes infinite, traces a complex shape around both mass concentrations. Background galaxies at different distances experience different levels of magnification. Objects near the critical curves can be magnified 30 to 100 times. Those farther away receive less amplification. Astronomers must carefully model the cluster's mass distribution to calculate magnification factors for each lensed galaxy. The modeling process uses confirmed multiple images as constraints. Spectroscopy provides redshifts for these images, confirming they are indeed multiple copies of the same background object. Over 100 spectroscopically confirmed multiple images help refine the model. The precision reaches remarkable levels, with position predictions accurate to fractions of an arcsecond. MAX J416 became a prime target for James Webb Space Telescope observations. Its proven lensing power, combined with Webb's infrared sensitivity, promised discoveries. The telescope pointed its instruments at the cluster field. Deep exposures captured light from some of the most distant galaxies ever observed. Hidden among those distant galaxies, magnified, and just barely bright enough to analyze, sat LAP-1b. But magnification alone does not explain how we decoded its secrets. Magnification sounds simple, make something appear bigger, but gravitational lensing involves physics far more complex than ordinary optics. The mathematics describes how space-time curvature alters photon paths. Each ray of light experiences slightly different deflection depending on its trajectory. The cluster's mass distribution determines lensing strength. Regions with higher mass density bend light more strongly. The deflection angle depends on the impact parameter, how close the light passes to the mass concentration. Small changes in position can dramatically affect magnification. Near the critical curves, magnification grows extreme. An object positioned right at the critical curve theoretically experiences infinite magnification. In practice, the object has finite size, so magnification remains large but finite. Values of 30 to 100 times are common for well-positioned background galaxies. LAP-1b sits in an optimal location. Its light passes close enough to one of the cluster's mass concentrations to receive strong lensing, but not so close that the image becomes too distorted to analyze. The magnification factor reaches approximately 100. That factor means critical differences. Without lensing, LAP-1b would appear 100 times dimmer. Webb's detectors would barely register it. Gathering enough photons for spectroscopy would require impossibly long exposures. The spectrum, revealing population 3 stars, would never exist. Magnification also stretches the image. Instead of appearing as a single point, the galaxy forms an arc, several arcseconds long. This distortion actually helps. The stretched image covers more detector pixels, improving signal measurement. Astronomers can analyze different regions of the arc separately. The lensing introduces complications, though. Magnification varies across the image. The side closer to the mass concentration gets amplified more than the far side. This differential magnification can distort measurements of the galaxy's intrinsic properties. Scientists must carefully model these effects. Time delays represent another consequence. Different images of the same object can appear at different times. Light following different paths around the lens takes different amounts of time to reach us. For strongly lensed systems, delays can range from days to years. Astronomers use these delays to measure cosmic expansion. The background galaxy's position matters enormously. Move it slightly and the magnification changes. A galaxy just half an arcsecond away might receive 10 times less amplification. The alignment between Earth, cluster, and LAP-1b happens to be nearly perfect. Pure cosmic luck. Astronomers calculate magnification using sophisticated lens models. These models incorporate the cluster's measured mass distribution. They account for contributions from individual galaxies, dark matter halos, and smooth dark matter components. Uncertainties in the model translate to uncertainties in magnification estimates. For LAP-1b, the model predicts magnification around 100 times. Different models give slightly different values, typically ranging from 70 to 130 times. All agree the amplification is substantial. All agree that without it, we could not study this galaxy in detail. The precision of modern lensing models has become remarkable. Root means square errors in predicted image positions reach only 0.4 arcseconds. That accuracy means magnification estimates are reliable to within roughly 10% for most images. For science, that precision suffices. Einstein's general relativity passes another test. The observed lensing matches predictions perfectly. Space-time curvature behaves exactly as the equations describe. What that magnification revealed in LAP-1b's spectrum changed everything. The galaxy designation reads LAP-1b. The letters and numbers mean nothing poetic, just another entry in astronomical catalogues. But this particular galaxy holds something no catalogue anticipated. Its light began traveling toward Earth 800 million years after the Big Bang. The universe itself was only 800 million years old when these photons started their journey. To put that in perspective, the universe is 13.8 billion years old today. We see LAP-1b as it existed during the first 6% of cosmic history. The photons traveled for 13 billion years. They crossed vast stretches of expanding space. As space expanded, their wavelengths stretched. What started as energetic ultraviolet radiation became infrared by the time it reached Webb's mirrors. This redshift allows astronomers to measure the galaxy's distance precisely. LAP-1b appears small. Its total stellar mass amounts to perhaps a few million times our star's mass. Modern galaxies contain hundreds of billions of stars. This is a dwarf by comparison. But size misleads. What matters is not how much mass, but what kind. The galaxy structure shows interesting features. Instead of a smooth disk or ellipse, it appears clumpy. Distinct regions of star formation create bright knots visible even in Webb's images. These knots might represent individual star clusters forming. Each cluster could contain several to a few dozen massive stars. Temperature measurements indicate extreme conditions. The stars within LAP-1b burn at surface temperatures around 90,000 degrees. Our nearest star's surface reaches only about 10,000 degrees. The difference is not subtle. These stars pour out vastly more ultraviolet radiation per unit area. The high temperature has consequences. Ultraviolet photons carry enough energy to ionize hydrogen atoms, stripping electrons away. Each massive star in LAP-1b produces enormous amounts of this ionizing radiation. The combined output from the entire galaxy floods its surroundings with high-energy photons. This flood drives a phase transition called reionization. Neutral hydrogen gas absorbs the ultraviolet light and becomes ionized plasma. A bubble of ionized gas expands around the galaxy. Eventually, bubbles from many early galaxies merge. The entire universe transitions from neutral to ionized. LAP-1b sits right at the era when reionization was happening. The cosmic dark ages were ending. Light was finally powerful enough to change the universe's state. This galaxy participated in that transformation. The spectrum provides the most crucial information. Specific wavelengths show emission lines from ionized helium. Helium normally requires very high temperatures to ionize twice, creating what astronomers call helium-2. Regular stars do not produce enough energy, but population 3 stars, with their extreme temperatures, can do it. The helium-2 emission appears strong in LAP-1b's spectrum. That single feature became the smoking gun. Combined with the lack of heavy element absorption lines, it points unmistakably toward primordial stars. Additional evidence comes from the emission line ratios. Different elements emit light at characteristic wavelengths when excited. The relative strengths of these lines reveal physical conditions. For LAP-1b, the ratios match predictions for gas surrounding extremely hot, massive stars. Astronomers checked alternative explanations. Could something else produce this spectrum? Perhaps a black hole accreting matter? The emission patterns do not match. Could it be contamination from a foreground source? The redshift rules that out. Every test points back to population 3 stars. The galaxy's age provides a timeline. 800 million years after the Big Bang, star formation was already well underway, but conditions still remained primitive. Not enough time had passed for many stellar generations. Heavy elements had not yet enriched the gas significantly. LAP-1b represents a snapshot, a moment when the universe was transforming but not yet transformed. Yet even this incredible discovery raises deeper questions about what came before. The Big Bang releases an inferno of energy. For 380,000 years, the universe remains too hot for atoms to form. Protons and electrons exist separately, creating a thick fog. Light cannot travel far before scattering. The cosmos glows like the surface of a star, opaque and blazing. Then expansion and cooling reach a threshold. Electrons combine with protons, forming neutral hydrogen atoms. This moment, called recombination, changes everything. Light suddenly travels freely. The fog clears. We detect those ancient photons today as the cosmic microwave background, arriving from all directions as faint radio whispers. But clearing the fog does not bring daylight. No stars exist yet. Galaxies have not formed. The universe enters a period astronomers call the cosmic dark ages. Darkness reigns for hundreds of millions of years. Only the slowly cooling glow of the Big Bang provides any illumination. During this darkness, gravity works silently. Tiny density variations, quantum fluctuations from the Big Bang, begin growing. Regions slightly denser than average attract more matter. Regions slightly less dense lose matter. The differences amplify over time. Dark matter drives this process. It makes up roughly 85% of all matter. Unlike ordinary matter, dark matter does not interact with light. It only interacts through gravity. This gives it an advantage. Without radiation pressure to resist collapse, dark matter starts clumping immediately after recombination. The clumps grow into structures called dark matter halos. These halos form at all scales, from small to enormous. The smallest halos that can trap gas and form stars have masses around 100,000 to 1 million times our star's mass. Astronomers call these mini-halos. Ordinary matter, mostly hydrogen and helium gas, falls into these dark matter gravitational wells. As gas falls inward, it heats up from compression. The temperature rises to thousands of degrees. At this point, the gas should cool and condense further to form stars. But cooling presents a challenge. Gas cools by emitting radiation. Atoms collide, become excited, then release photons as they de-excite. Heavy elements with many electrons provide efficient cooling. They have numerous energy levels that can radiate across many wavelengths. But the primordial gas contains almost no heavy elements. Hydrogen and helium cooling works differently. Individual atoms do not radiate efficiently. Instead, molecules of hydrogen, where two hydrogen atoms bond together, become crucial. These molecules can vibrate and rotate, emitting infrared photons. Molecular hydrogen formation allows the gas to cool enough for star formation. The formation rate of molecular hydrogen proceeds slowly. Two hydrogen atoms rarely stick together on their own. They need a surface to facilitate bonding, like dust grains. But the early universe has virtually no dust. Alternative formation pathways exist, involving free electrons and hydrogen ions, but they are inefficient. This inefficiency has profound consequences. The gas cannot cool quickly or to low temperatures. It cannot fragment into many small clumps. Instead, the entire halo cools as one large mass. When collapse finally accelerates and star formation begins, it creates just one or a few very massive stars. The timeline stretches. Recombination happens at 380,000 years after the Big Bang. The first stars do not ignite until approximately 200 million years later. 400 million years of darkness pass before the universe's first light switches on. Imagine the weight. Gravity pulling matter together, gas falling into invisible halos, pressure building, temperature rising, molecular hydrogen slowly accumulating, density increasing. The universe poised on the edge of transformation. Then somewhere, in some mini-halo, the center becomes dense enough. Nuclear fusion ignites. What happened at that moment shaped everything that followed. The first cloud to collapse contains an inventory we can list completely. 75% hydrogen by mass, 25% helium, trace amounts of lithium, barely worth mentioning. That is everything. No carbon, no nitrogen, no oxygen, no silicon, no iron, nothing heavier than helium except those few lithium atoms. This composition seems unremarkable. It is simply what the Big Bang produced. But that simplicity creates extraordinary consequences for star formation. Modern star-forming clouds contain dust grains made of carbon, silicon, oxygen, and other elements, fill the space between stars. These grains serve critical functions. They shield forming stars from radiation. They provide surfaces where molecules can form. Most importantly, they radiate infrared light efficiently, cooling the gas. Cooling determines fragmentation. If gas cools quickly, it breaks into many small clumps. Each clump might form a star. Fast cooling produces numerous low-mass stars. Slow cooling keeps the gas in larger clumps. Those large clumps produce fewer, more massive stars. Heavy elements accelerate cooling. They have complex electron structures with many energy levels. Collisions can excite these levels. De-excitation releases photons at many wavelengths. Each photon carries away energy, cooling the gas. The primordial gas lacks these cooling mechanisms. Hydrogen and helium atoms have simple structures with few transitions. Molecular hydrogen helps, but only in the infrared. The cooling rate stays much lower than in modern clouds. Lower cooling rate means higher temperature. The gas in mini-halos settles at temperatures around 1000 to 3000 degrees. Modern star-forming clouds reach 10 to 100 degrees. The difference fundamentally changes the physics. Hotter gas has higher pressure. Pressure resists gravity. To overcome that pressure, the collapsing region must be more massive. The minimum mass for collapse increases with temperature. Calculations show that primordial clouds require much more mass before they can fragment and form stars. This leads directly to higher stellar masses. Instead of forming stars like our own, with masses around 1 to 10 times our star's mass, primordial clouds form monsters. Typical masses range from 30 to 300 times our star's mass. Some models predict even larger objects, reaching 1,000 times our star's mass. The chemistry, or lack thereof, affects another crucial process. Heavy elements increase the opacity of stellar material. They absorb radiation passing through the gas. Higher opacity means radiation gets trapped more easily. Trapped radiation heats the material and creates pressure that resists further collapse. With almost zero heavy elements, primordial material has extremely low opacity. Radiation escapes easily. Without radiation pressure to halt the collapse, more mass can accumulate. The forming star grows larger before reaching equilibrium. The magnetic field strength also depends on composition. Heavy elements carry more electrons, facilitating ionization. Ionized gas interacts with magnetic fields. The primordial gas ionizes less easily. Magnetic fields develop differently. This changes how angular momentum gets transported during collapse. Everything ties back to that simple inventory: hydrogen and helium only. The absence of heavier elements is not a minor detail. It is the defining characteristic. It determines that the first stars will be massive. It guarantees they will live fast. It ensures they will die explosively. The universe had to start this way. No other option existed. The Big Bang nucleosynthesis could not produce heavy elements. Only stars can forge them through nuclear fusion. But to build the first stars, you need only hydrogen and helium. It creates a bootstrap problem with a violent solution. Star formation follows rules written by gravity and thermodynamics. Gas collapses, density increases, temperature rises. Eventually, the core becomes hot enough for nuclear fusion. Hydrogen nuclei, overcome their electromagnetic repulsion, and combine, energy releases. A star is born. Those basic steps never change, but the details vary enormously depending on the gas composition. Modern stars form according to a well-tested recipe, refined over billions of years. Primordial stars have no such recipe. They are improvising. Consider what modern star formation looks like. A cold molecular cloud, temperature around 20 degrees above absolute zero. The cloud contains complex molecules, carbon monoxide, water, ammonia. Dust grains pervade the medium. Magnetic fields thread through the structure. Turbulence creates dense regions where gravity overcomes pressure. A region begins collapsing. As it shrinks, it heats. But dust radiates the heat away efficiently. The temperature stays low. More mass accumulates. The collapsing region breaks into multiple fragments. Each fragment will become a star. The fragments continue collapsing. A protostar forms at the center, surrounded by a rotating disk of material. The disk feeds matter onto the protostar gradually. Magnetic fields and jets help shed angular momentum. The star grows slowly over hundreds of thousands to millions of years. Eventually, the core temperature reaches 10 million degrees. Hydrogen fusion ignites. Radiation pressure from the fusion reactions halts further collapse. The star settles into a stable configuration, fusing hydrogen in its core. This stable phase lasts billions of years for stars like our own. Now contrast this with primordial star formation. The cloud starts much hotter, thousands of degrees instead of tens. No dust exists to radiate heat efficiently. Molecular hydrogen provides the only significant cooling, and it works slowly. The cloud does not fragment into many pieces. It remains coherent. The collapse proceeds faster. With less pressure support, gravity accelerates the infall. Material rushes toward the center. A protostar forms, but it is already massive. The surrounding envelope continues feeding it at high rates. Instead of a thin disk, thick flows of gas spiral inward. The protostar grows rapidly. Within just 10,000 to 100,000 years, it might accumulate 30 to 100 times our star's mass. The growth rate exceeds modern star formation by orders of magnitude. Nothing limits the accretion except the radiation pressure from the forming star. The core reaches fusion temperatures quickly, but fusion ignition does not immediately halt growth. The radiation struggles to escape through the opaque infalling envelope. The star becomes bloated with a huge radius. Its surface temperature stays relatively cool despite the enormous power output. As accretion slows, the star contracts. The radius shrinks. Surface temperature rises dramatically. Eventually, the star reaches the main sequence, the stable phase, where it fuses hydrogen in its core. But it reaches that phase as a behemoth. The final mass depends on exactly when accretion stops. Different scenarios produce different outcomes. If gas continues flowing unabated, the star might reach several hundred times our star's mass. If early radiation pushes away remaining gas, the star might settle at 30 to 100 times our star's mass. Computer simulations struggle to capture all the physics. The calculations require tracking dynamics over huge ranges of scale, from giant molecular clouds spanning light years to stellar cores measured in thousands of miles. The computations take months on supercomputers. Different research groups get somewhat different results. Some models produce mostly stars around 100 times our star's mass. Others predict a broader range. A few suggest some regions might form smaller stars alongside the giants. The uncertainty reflects genuine complexity, but all models agree on the essential point. Primordial stars form more massive than modern stars. The typical mass exceeds 30 times our star's mass. Many reach 100 to 300 times our star's mass. These are not normal stars. The absence of heavy elements does not just affect formation. It shapes every aspect of the star's life. Starting with how violently they burn, mass controls everything about a star's life. How brightly it shines, how fast it burns fuel, how long it lives, how it dies. A star with 100 times our star's mass lives a completely different existence. Our nearest star provides the baseline. Its mass defines one solar mass, the unit astronomers use. Its luminosity defines one solar luminosity. Its lifetime, about 10 billion years total, spans most of cosmic history. It is stable, predictable, ordinary. Now scale up by a factor of 100. The mass increases linearly, 100 solar masses, but luminosity does not scale linearly. It scales according to a steep power law. For very massive stars, luminosity increases roughly as mass to the third power. The calculation reveals something shocking. A star with 100 times our star's mass shines approximately 1 million times brighter. Not 100 times, not 10,000 times, 1 million times. The radiation output becomes almost incomprehensible. This extreme luminosity creates immediate consequences. Radiation pressure pushes outward on the star's material. Every photon carries momentum. When atoms absorb those photons, they feel a force. With enough photons streaming outward, the radiation pressure can overcome gravity. The balance becomes precarious. Gravity tries to hold the star together. Radiation pressure tries to blow it apart. For stars above a certain mass, roughly 150 to 200 times our star's mass, radiation pressure might actually win. The star becomes unstable. It cannot maintain a stable structure. It might pulsate violently or even disrupt. Population. 3 stars with masses around 100 times our star's mass sit just below this limit. They manage to hold together, barely. The pressure balance remains stable, but only just. Any slight perturbation could trigger instability. The star's core operates under extreme conditions. Temperature reaches tens of millions of degrees. Density exceeds 100 grams per cubic centimeter, making water seem like vacuum by comparison. At these conditions, nuclear fusion proceeds at ferocious rates. The fusion process follows well-understood reactions. 4 hydrogen nuclei combine through several intermediate steps to form one helium nucleus. The mass of the helium nucleus is slightly less than the combined mass of 4 hydrogen nuclei. That missing mass converts to energy via Einstein's equation. For our nearest star, this process runs steadily for billions of years. The fusion rate stays constant. The energy output stays stable. For a 100 solar mass star, the fusion rate accelerates dramatically. More mass means more fuel. Higher temperature means faster reactions. The star burns through its hydrogen supply at a prodigious rate. The lifetime shortens accordingly. Our nearest star will spend about 10 billion years fusing hydrogen in its core. A star with 100 times our star's mass exhausts its core hydrogen in approximately 2 to 3 million years. The factor is roughly 5,000 times shorter. Think about that timescale. Humans have been anatomically modern for about 300,000 years. Recorded history spans 5,000 years. These massive stars live and die faster than human civilization has existed. Their life cycle rushes past in cosmic instants. Main sequence hydrogen burning, 2 million years. Shell hydrogen burning, perhaps 200,000 years. Helium core burning, even shorter. The star races through every evolutionary phase. The surface characteristics reflect the interior violence. Temperature at the photosphere, the visible surface, reaches 80 to 100,000 degrees. The star glows intensely blue-white. Almost all its radiation emerges as ultraviolet light. The visible light output, while still enormous, represents only a tiny fraction of total luminosity. This ultraviolet flood affects everything nearby. Gas within hundreds of light years gets ionized. Dust grains, if any existed, would be destroyed by the harsh radiation. Other forming stars in the vicinity feel the radiation pressure. Star formation in the surrounding region might be suppressed or even halted. The stellar wind adds another effect. Hot, massive stars drive powerful winds through radiation pressure. Gas at the surface absorbs photons and accelerates outward. The wind carries away mass. For the most massive population 3 stars, wind mass loss rates might reach significant fractions of the star's total mass over its lifetime. This mass loss affects evolution. It reduces the final mass before supernova. It changes the structure of the outer layers. It enriches the surroundings with partially processed material. Every aspect of the star's behavior amplifies with mass. More luminosity, hotter surface, faster fusion, stronger wind, shorter life. The scaling laws of stellar physics drive everything toward extremes. But even these extremes only hint at what happens at the surface. Temperature defines how matter behaves. At room temperature, 300 degrees above absolute zero, atoms move sluggishly. Chemical bonds form. Solids and liquids exist. At a few thousand degrees, most atoms ionize. Electrons break free. Matter becomes plasma. At 90,000 degrees, the rules change completely. The photosphere, the layer of a star we see, has a characteristic temperature. For our nearest star, that temperature measures about 5,800 degrees. The star appears yellow because peak radiation emerges at wavelengths corresponding to yellow light. The Wien displacement law connects temperature to color. For population 3 stars with 90,000 degree surfaces, the peak wavelength shifts deep into ultraviolet. The visible spectrum receives only a small fraction of the total emission. These stars would look intensely blue-white to human eyes, if eyes could tolerate the ultraviolet radiation without instant damage. The photosphere temperature depends on the energy flux escaping from deeper layers. Energy generated by core fusion diffuses outward. The radiation works its way through the stellar material, getting absorbed and re-emitted countless times. Eventually, it reaches the surface. At the photosphere, the material becomes transparent enough for radiation to escape into space. The temperature at this boundary determines the star's effective temperature. Massive stars with high luminosity must have hotter surfaces to radiate all that energy. The 90,000 degree temperature creates specific ionization states for atoms. Hydrogen loses its single electron completely. Only bare protons remain. Helium loses both electrons, becoming doubly ionized. Any trace amounts of heavier elements present lose most or all electrons. These ionization states determine the spectrum we observe. Ionized hydrogen cannot absorb light the same way neutral hydrogen does. The absorption lines shift to different wavelengths. Doubly ionized helium creates distinctive emission lines that singly ionized helium cannot produce. The helium-2 emission line becomes diagnostically crucial. It requires ionization energies around 54 electron volts. Normal stellar temperatures cannot provide enough energy to create significant amounts of doubly ionized helium, but 90,000 degrees suffices. The thermal energy of the gas matches the ionization energy. When astronomers observe strong helium-2 emission, they immediately know something extraordinarily hot is present. Possible sources include extremely massive stars, intense shock waves, or gas near black holes. For LAP-1b, the spectral signature points to massive hot stars. The high surface temperature affects stellar winds. Radiation pressure on metal ions drives winds in normal massive stars. But primordial stars have almost no metals. Instead, radiation pressure acts on electrons through Thomson scattering. Photons collide with free electrons, transferring momentum. With so many high-energy photons streaming outward, the Thomson scattering effect becomes strong. Electrons accelerate outward. They collide with protons, dragging them along. The wind develops, flowing away from the star at speeds reaching thousands of miles per second. The wind mass loss rate scales with luminosity and surface temperature. Higher luminosity means more photons to push material. Higher temperature means the photosphere sits farther out in radius, making the escape easier. Population. 3-star winds might remove several % of the star's mass over its lifetime. This wind enriches the surrounding medium before the star even explodes. Processed material from the stellar interior gets mixed to the surface through convection, then blown away by the wind. The first heavy elements begin spreading even before the first supernova. The intense radiation also drives a process called photoevaporation in nearby gas clouds. Ultraviolet photons hit neutral hydrogen atoms with enough energy to ionize them. The ionized gas heats rapidly. It expands and flows away. Clouds that might have formed additional stars get disrupted. Single population. 3 stars might ionize and heat gas over regions hundreds of light years across. Multiple stars amplify the effect. Small clusters containing just 3 to 10 such massive stars can impact an entire mini-halo. Temperature at 90,000 degrees represents the visible face of the interior inferno. But to understand the true violence, we must look at how fast the core burns, which happens to be the fastest burn rate in cosmic history. Fusion rate depends on temperature with extreme sensitivity. The reaction probability increases rapidly as temperature rises. For the proton-proton chain that powers our nearest star, the rate scales approximately as temperature to the 4th power. Small temperature increases produce large rate increases. The core of our nearest star operates at about 15 million degrees. At this temperature, fusion proceeds steadily but slowly. Each second, roughly 600 million tons of hydrogen converts to helium. That sounds like a lot. It is not. Our nearest star contains more than 2 billion tons of hydrogen. The fuel will last 10 billion years. Population 3 star cores reach temperatures around 50 to 100 million degrees. The temperature increase factor is roughly 4 to 6, but the fusion rate does not increase by just 4 to 6 times. Remember the power law scaling. Temperature to the 4th power means the rate increases by about 250 to 1300 times for that temperature increase alone. But temperature is not the only factor. Density matters too. Higher density means more hydrogen nuclei packed into each cubic centimeter. More particles mean more collisions. More collisions mean more fusion reactions. Population. 3 star cores reach densities 10 to 100 times higher than our nearest star's core. Multiply the temperature effect by the density effect. The fusion rate per unit volume exceeds our nearest star's core by factors of thousands to hundreds of thousands. Now multiply by the star's total mass. A 100 solar mass star has 100 times more hydrogen fuel, but it burns that fuel millions of times faster. The numbers lead to an inescapable conclusion. These stars exhaust their core hydrogen in about 2 to 3 million years. Our nearest star takes 10 billion years. The ratio exceeds 3,000. Population. 3 stars live fast, at a pace that defies intuition. The rapid fusion has another consequence. The energy generation rate per gram of material becomes extreme. More power packed into the same volume means higher pressure. The core inflates slightly. The star adjusts its structure to maintain equilibrium. This adjustment affects the surface properties. Higher core energy generation eventually translates to higher surface luminosity. The star must radiate away all the energy produced in the core. A 100 solar mass population, 3 star shines with the light of approximately 1 million stars like our own. The core composition changes rapidly too. Hydrogen converts to helium. The helium accumulates, creating a growing helium core. As the core becomes more helium-rich, the hydrogen fusion reactions migrate outward into a shell surrounding the core. Shell hydrogen burning introduces instabilities. The shell can burn unevenly. Pulses of energy generation occur. The star's structure responds with variations in radius and temperature. Some models predict these variations could drive pulsations, making the star's luminosity fluctuate. When core hydrogen exhausts, a new phase begins. The helium core contracts and heats. Eventually, it becomes hot enough for helium fusion. 3 helium nuclei combine to form carbon. Additional reactions produce oxygen. Heavier elements start appearing. Helium burning proceeds even faster than hydrogen burning. It requires higher temperatures, around 100 to 200 million degrees. At these temperatures, nuclear reaction rates skyrocket. The star burns through its helium in perhaps 200,000 years. After helium comes carbon burning, then neon burning, then oxygen burning. Each successive stage runs hotter and faster. Carbon burning might last 20,000 years. Oxygen burning lasts just 1 year. Silicon burning, the final stage before iron, lasts about 1 day. The star builds up a layered structure, an iron core surrounded by silicon shell, surrounded by oxygen shell, surrounded by neon shell, surrounded by carbon shell, surrounded by helium shell, surrounded by hydrogen envelope. Each layer burns when conditions are right. The progression marches inward through the periodic table. Iron represents the end. Fusion of nuclei lighter than iron releases energy. Fusion of nuclei heavier than iron requires energy input. Once the core converts to iron, no further energy generation is possible. The core is thermally dead, but the rest of the star does not know this yet. The outer shells keep burning and dumping mass onto the core. The iron core grows, its mass increases, and it approaches a critical threshold. What happens when that threshold is crossed determines whether the universe gets its first heavy elements. Spectroscopy splits light into its component wavelengths. Each element absorbs or emits light at specific wavelengths, determined by quantum mechanics. These wavelengths create a unique fingerprint. Read the fingerprints correctly, and you decode what materials exist, their temperatures, their motions, their abundances. Webb's near-infrared spectrograph, called NIRSpec, captured the spectrum of LAP 1b. The exposure required hours of telescope time. Photons from the distant galaxy accumulated slowly on the detectors. Eventually, enough signal gathered to extract meaningful data. The spectrum shows a series of emission lines. Bright features at specific wavelengths where the galaxy emits strongly. The strongest line corresponds to hydrogen alpha, produced when hydrogen electrons transition between energy levels. Its presence and strength indicate hot gas, ionized by stellar radiation. Other lines appear at wavelengths corresponding to helium, both singly and doubly ionized. The helium-2 line becomes the critical feature. This emission requires temperatures around 90,000 degrees or higher. Only the hottest massive stars, certain shock waves, or accretion disks around black holes can produce these conditions. Conspicuously absent are lines from heavy elements. No oxygen, 2 or 3. No carbon, 3 or 4. No nitrogen. No neon. No iron. The spectrum appears remarkably clean, dominated by hydrogen and helium with minimal metal contamination. Astronomers measure element abundances using line strengths. The intensity of each line depends on the abundance of that element, the temperature and density of the gas, and the ionization conditions. Sophisticated models connect observed line strengths to physical parameters. For LAP 1b, the models reveal extremely low metallicity. The abundance of elements heavier than helium measures at least 1,000 times lower than our nearest star's atmosphere. This places LAP 1b's gas composition very close to primordial. The heavy element enrichment from previous stellar generations appears minimal or absent. The emission line ratios provide another diagnostic. Different lines respond differently to temperature, density, and ionization parameter. By comparing line strengths, astronomers constrain these physical conditions without knowing absolute abundances. LAP 1b's line ratios indicate gas with very high ionization parameter. This means intense radiation field relative to gas density. Such conditions arise naturally around extremely hot, luminous stars. The gas gets flooded with ultraviolet photons, ionizing it completely and maintaining high temperatures. The researchers also measure the velocity dispersion from line widths. Broader lines indicate faster gas motions. LAP-1b shows relatively narrow lines, suggesting the gas has not been stirred by violent feedback yet. The system appears young, with star formation recently initiated. One specific test proved crucial. Could any other phenomenon besides population 3 stars produce this spectrum? The team systematically ruled out alternatives. Active galactic nucleus. The emission patterns do not match. Quasar spectra look different. The line ratios are wrong. Normal metal-poor stars? Even very metal-poor stars contain detectable oxygen and carbon. LAP-1b shows virtually none. Shock heating? Shocks can produce helium-2 emission, but the other line ratios would differ. LAP-1b's spectrum does not resemble known shock-heated systems. Each alternative fails some diagnostic test. The spectrum uniquely matches predictions for gas ionized by very hot, very massive, very metal-poor stars. The theoretical models developed decades ago anticipated exactly this signature, but spectrum alone does not prove the case. Astronomers needed to check 3 specific theoretical criteria. These criteria represent the gold standard for population 3-star identification. Meeting all 3 would elevate the detection from interesting to definitive. First criterion: the gas must have primordial composition, metallicity, below 1/1000th our star's value. LAP-1b passes. Its spectrum shows essentially no heavy elements. Second criterion: the stars must form in low-mass structures consistent with mini-halos. Total stellar mass of only a few million solar masses. LAP-1b passes. Its brightness and size indicate a small galaxy. Third criterion: the initial mass function must be consistent with forming very few very massive stars. Not a full population of stars at all. Masses like modern systems. LAP-1b passes. The emission properties suggest at most a few dozen massive stars, not millions of low-mass stars. All 3 criteria satisfied. The statistical probability of this combination occurring by chance approaches 0. LAP-1b contains population 3 stars. Confirmed. The detection represents the culmination of decades of searching. Hundreds of papers predicted what these stars should look like. Observers scrutinized countless galaxies, looking for the signature. Finally, Webb's sensitivity and gravitational lensing magnification combined to reveal the prize. But knowing population 3 stars exist only opens deeper questions. How exactly did they burn? What processes occurred in their cores? The answers require understanding nuclear fusion at its most extreme. Previous claims of population 3-star detections existed. Several research groups announced possible discoveries using Hubble and ground-based telescopes. Each claim generated excitement. Each claim also generated skepticism. The evidence never quite met the highest standards. Ambiguities remained. Alternative explanations could not be ruled out completely. The Visbal team's approach differed. They established 3 rigorous theoretical criteria before claiming detection. Any candidate must satisfy all 3. Partial matches do not count. These criteria emerged from decades of computer simulations and theoretical work. Researchers modeled population 3-star formation in detail. The simulations tracked dark matter halo growth, gas cooling, molecular hydrogen chemistry, and eventual star formation. From this work, clear predictions emerged about where and how these stars should appear. First condition: low metallicity environment. Population: 3 stars by definition form from primordial gas. The Big Bang produced hydrogen, helium, and trace lithium. Subsequent nuclear fusion in stars created heavier elements. If significant metal enrichment occurred before star formation, the resulting stars would be population 2, not population 3. The metallicity threshold matters. Exactly how metal-poor must the gas be? Theoretical work shows that even tiny amounts of carbon or oxygen dramatically enhance cooling. Metallicity above 1/1000th solar allows efficient cooling and fragmentation. This produces normal stars, not giants. LAP-1b shows metallicity well below 1/1000th solar. Most heavy elements appear absent entirely from the spectrum. The gas composition approaches primordial. First condition satisfied. Second condition: small cluster mass. Population: 3 stars form in mini-halos, with masses around 100,000 to 1 million solar masses. Larger halos, with masses above 1 million solar masses, develop different dynamics. The gas can cool more efficiently. Multiple stellar generations might form. The environment becomes more complex. LAP-1b's total stellar mass estimates come in around a few million solar masses. This fits the predicted range for mini-halo star formation. The galaxy appears compact. No evidence suggests it has merged with larger systems or undergone extensive evolution. Second condition satisfied. Third condition, top-heavy initial mass function. The initial mass function describes the distribution of stellar masses at birth. Modern star formation produces a broad range. Most stars form with masses below our nearest star's mass. Only rare stars reach 10 or 20 solar masses. Population 3 formation differs fundamentally. Without efficient cooling, fragmentation barely occurs. Only one or a few objects form per cloud. Those objects accumulate large masses. The initial mass function becomes top-heavy, concentrated at high masses. LAP-1b's observed properties indicate very few stars. The helium-2 emission and high ionization parameter require intense radiation. This comes from perhaps 3 to 30 extremely massive stars, not millions of stars spanning all masses. The mass distribution must be heavily weighted toward giants. Third condition satisfied. Previous candidate detections satisfied one or two conditions, but not all three. A galaxy might show low metallicity but have evidence for multiple stellar generations. Another might appear young but show metallicity too high. The combinations always fell short. LAP-1b represents the first object meeting every criterion simultaneously. The probability of accidental alignment is negligible. Statistical analysis confirms significance exceeds 5 sigma, the gold standard in physics, for discovery claims. The mathematical formalism involves Bayesian inference. Researchers calculate the likelihood of observing LAP-1b's properties under different scenarios. Population, 3-star model, high likelihood. Normal star formation model, extremely low likelihood. Alternative explanations, all low likelihood. The population 3 interpretation wins overwhelmingly. The discovery paper underwent rigorous peer review. Multiple expert referees examined the data, analysis, and conclusions. Requests for additional tests and alternative explanations had to be addressed. Only after satisfying reviewers did the journal accept publication. Publication in the Astrophysical Journal Letters represents validation by the scientific community. The journal publishes only high-impact discoveries. The editors judged this work met that standard. Other research groups have begun analyzing the same data independently. So far, preliminary results support the original findings. The spectrum behaves as reported. The 3 conditions hold. LAP-1b genuinely appears to host population 3 stars. The detection opens a new observational window. Astronomers now know what to look for and where to look. More candidates will emerge from Webb data. Gravitationally lensed fields offer the best targets. The search accelerates. But identifying these stars only begins the story. Understanding what happens inside them requires diving into nuclear physics. The core exhausts its hydrogen fuel first. Temperature and density reach their maximum at the center. Fusion proceeds fastest there. The helium ash accumulates. Hydrogen burns out from the inside. A strange situation develops. The core now contains mostly helium. Helium does not fuse at 15 to 50 million degrees. It requires higher temperatures, around 100 to 200 million degrees. The core cannot generate energy yet. It becomes inert. But the star still contains vast amounts of hydrogen in layers surrounding the core. That hydrogen reaches sufficient temperature and density to fuse. Nuclear reactions ignite in a shell around the inert helium core. The star enters shell hydrogen burning phase. Shell burning behaves differently from core burning. The geometry matters. In the core, fusion occurs throughout a large volume. Energy generation spreads over the whole core. In a shell, fusion occurs in a thin layer. Energy generation concentrates in that narrow region. Concentrated energy generation creates instabilities. Slight increases in temperature accelerate fusion rate. More fusion releases more energy. Energy increases temperature further. A runaway develops. The shell burns in pulses rather than steadily. These pulses drive structural changes. When the shell burns vigorously, Extra energy pushes the overlying layers outward. The star's radius increases. Surface temperature drops slightly. When the shell quiets, the envelope contracts. The cycle repeats. For population 3 stars, shell burning proceeds explosively fast. Remember the mass and temperature scalings. These stars already burn millions of times faster than our nearest star. Shell burning amplifies the speed further. The shell dumps helium onto the core continuously. Fusion products from the shell settle inward due to gravity. The helium core mass grows. It shrinks as mass adds, becoming denser and hotter. Eventually, it reaches the helium fusion threshold. Helium fusion begins suddenly. 3 helium nuclei must collide nearly simultaneously to form carbon. This triple alpha process requires precise conditions. Temperature must exceed 100 million degrees. Density must be high enough that 3 particle collisions occur frequently. When conditions are met, helium ignites. The core springs to life. Carbon and oxygen form from helium. New nuclear energy pours out. The star adjusts its structure again. The hydrogen shell continues burning in the outer layers. Now, the star has 2 active burning regions. Helium fusion in the core, hydrogen fusion in a shell above the core. Both proceed at furious rates. The timescale for helium core burning might be just 200,000 years. During helium burning, the core contracts slightly but remains stable. The star's luminosity stays extremely high. The surface temperature hovers around 90,000 degrees. To external observers, little seems to change. Inside, the nuclear processes march relentlessly onward. Helium exhaustion arrives quickly. The core now contains carbon and oxygen. Again, these elements require even higher temperatures to fuse. The core becomes inert once more. Helium burning shifts to a shell surrounding the carbon-oxygen core. The star now has 3 layers: carbon-oxygen core, helium-burning shell, hydrogen-burning shell. Both shells contribute energy. The structure becomes complex and potentially unstable. Computer models struggle to follow this phase accurately. The calculations must resolve thin shells while tracking the entire star. Instabilities can develop. Convection zones appear and disappear. The star might pulse. Small numerical errors can compound into large uncertainties. Despite uncertainties, the overall progression remains clear. Each successive burning stage runs hotter and faster. Carbon burning comes next, lasting perhaps 20,000 years. Neon photodisintegration follows, then oxygen burning for about 1 year. Finally, silicon burning for approximately 1 day. Each stage produces heavier elements. Carbon burning makes neon and magnesium. Oxygen burning creates silicon and sulfur. Silicon burning assembles iron group elements. The star builds an onion-like structure with layers of different composition. The progression accelerates exponentially. Billion years, million years, 100,000 years, 10,000 years, days. The clock speeds up with each stage. The star races toward a critical threshold. When the iron core mass reaches approximately 1.4 solar masses, gravity overwhelms all other forces. Stability vanishes in an instant. The universe, after recombination, contains mostly neutral hydrogen. Electrons orbit protons as complete atoms. This neutral gas fills all of space. It absorbs ultraviolet light efficiently. Any photon with enough energy to ionize hydrogen gets absorbed quickly. This absorption creates a problem for distant observations. Light from the earliest stars travels through neutral hydrogen gas. The gas absorbs the ultraviolet photons. Only infrared light, which cannot ionize hydrogen, passes through unimpeded. The universe is effectively opaque to ultraviolet radiation. Then the first stars ignite. Each massive population, 3-star, produces prodigious amounts of ultraviolet photons. These photons stream outward at light speed. They strike neutral hydrogen atoms. The atoms absorb the photons and become ionized. An electron leaves. A free proton and free electron remain. Ionized hydrogen. a plasma, behaves completely differently from neutral hydrogen. Plasma does not absorb ultraviolet light the same way. The photons pass through more easily. A bubble of ionized gas forms around each star. The bubble expands. More photons ionize more atoms. The boundary between ionized and neutral gas moves outward. Eventually, the expanding bubble encounters another bubble from a different star. The bubbles merge. The ionized region grows. As more stars form throughout the universe, more bubbles appear. They expand, overlap, and merge. After hundreds of millions of years, the bubbles fill most of space. The universe transitions from mostly neutral to mostly ionized. This transformation is called reionization. The timeline matters. Reionization begins when the first stars form, approximately 200 to 400 million years after the Big Bang. It completes around 1 billion years after the Big Bang. The exact timing depends on how many ionizing photons the first stars produce. Population. 3 stars generate far more ionizing photons than normal stars. Their extreme temperatures, around 90,000 degrees, shift their emission into deep ultraviolet. The photon energies exceed hydrogen's ionization threshold by wide margins. Each massive star ionizes a region hundreds of light years across. A small cluster of just 10 such stars can ionize an entire mini-halo and beyond. The efficiency far exceeds what later stellar populations achieve. Observations constrain reionization history. The cosmic microwave background shows a specific polarization pattern caused by scattering off free electrons during reionization. Distant quasars reveal that the universe was mostly ionized by redshift 6, corresponding to roughly 1 billion years after the Big Bang. LAP-1b exists right in the middle of the reionization epoch. We see it at redshift 6.6, when the universe was 800 million years old. Reionization is actively happening. Some regions have ionized, others remain neutral. The process is incomplete. The galaxy sits inside its own ionized bubble, the population. 3 stars have cleared the gas in their immediate surroundings, but beyond that bubble, neutral hydrogen still dominates. The photons from LAP-1b can escape their local bubble, but then get absorbed by the neutral intergalactic medium. This absorption affects what we observe. Only photons with wavelengths longer than the Lyman alpha line can reach us from this epoch. Shorter wavelengths get blocked by neutral hydrogen. Astronomers call this the Gunn-Peterson trough. It appears as complete absorption at wavelengths shorter than Lyman alpha in distant galaxy spectra. Webb's spectrum of LAP-1b shows this effect. Emission lines redwood of Lyman alpha appear clearly. Bluewood of Lyman alpha, the spectrum drops to 0. The neutral hydrogen between LAP-1b and Earth blocks those photons. Reionization does not happen uniformly. Some regions ionize first, where star formation is most active. Other regions lag behind. The process proceeds in a complex, 3-dimensional pattern. Computer simulations attempt to capture this complexity. By observing many galaxies at different redshifts, astronomers map reionization progress. The neutral fraction decreases gradually from redshift 10 to redshift 6. By redshift 5, the universe is mostly ionized. Reionization completes. Population. 3 stars likely dominate the early phase. Their efficiency at producing ionizing photons means relatively few are needed. As metal-enriched population 2 stars form, they take over. Eventually, normal galaxies maintain the ionization against recombination. The reionization epoch represents a major phase transition. It changes the universe from opaque to transparent for ultraviolet light. It enables later galaxy formation by heating and stirring the intergalactic medium. It marks the end of the cosmic dark ages. LAP-1b provides a window into this critical era. We see reionization in action. The first light is transforming the cosmos. But light alone does not explain what happens when these stars finally die. Iron core grows. Silicon shell dumps more iron onto it. The mass approaches 1.4 solar masses. At this threshold, electron degeneracy pressure can no longer support the core. Gravity wins. The core collapses. Collapse happens fast. free fall timescale for a stellar core measures in fractions of a second. The entire core, initially about the size of Earth, shrinks to 20 miles across in less than 1 second. Density skyrockets to nuclear matter density. The collapse halts when nuclei touch each other. At this density, the strong nuclear force creates enormous repulsion. The core bounces, a shock wave forms, and propagates outward. This shock carries tremendous energy. When it reaches the star's surface, the star explodes. This is a core collapse supernova. For stars with masses below roughly 130 solar masses, this scenario describes the death, but population 3 stars often exceed this mass. Above 140 solar masses, a different process takes over. In extremely massive stars, core temperature reaches billions of degrees before ion production. At these temperatures, photons carry enormous energy. Gamma-ray photons can spontaneously convert into electron-positron pairs. Light becomes matter. This pair production removes energy from the radiation field. Pressure support drops suddenly. The core becomes unstable. It begins collapsing while still burning lighter elements. The collapse heats the material further. Burning accelerates catastrophically. Oxygen and silicon fuse explosively. The entire core burns to iron in seconds. The energy release is staggering. Instead of a gradual core collapse, the entire star explodes from runaway thermonuclear burning. This is a pair instability supernova. Pair instability supernovae differ fundamentally from core collapse supernovae. No remnant remains. The explosion completely disrupts the star. Every atom gets ejected into space. No neutron star. No black hole. Just an expanding cloud of gas. The energy released exceeds core collapse supernovae by factors of 10 or more. A typical core collapse supernova releases about 1 pho of energy, where 1 pho equals 10 to the 51 ergs. Pair instability supernovae can release up to 100 phos. This energy drives the ejector to high velocities. Gas speeds exceed 10,000 miles per second. The kinetic energy alone rivals the explosion energy of normal supernovae. The ejector sweeps up surrounding material, creating a massive bubble. The nucleosynthesis differs too. Core collapse supernovae produce elements through explosive burning in the shock. The precise abundance patterns depend on shock properties. Pair instability supernovae burn the entire core to ion group elements. Then the explosion synthesizes heavier elements through neutron capture. The resulting abundance pattern has distinctive features. Very high ratios of ion group elements to lighter elements. Enhanced production of certain isotopes like nickel-56. Unusual ratios of elements like magnesium to iron. Astronomers search for these abundance patterns in metal-poor stars. If population 3 stars exploded as pair instability supernovae, their ejector should have enriched later generations. Some metal-poor stars might preserve those abundance signatures. Several candidate stars have been identified. Their spectra show unusual ratios consistent with pair instability enrichment. The evidence remains suggestive rather than definitive. More observations are needed. The mass range for pair instability supernovae is narrow. Below 140 solar masses, the core collapses before pair production becomes important. Above about 260 solar masses, the star becomes unstable earlier and might not reach the pair instability regime. The window spans 140 to 260 solar masses. Stars in this range explode completely. Nothing remains. Every atom gets recycled. The iron, oxygen, carbon, and all other elements disperse into the interstellar medium. Future stars will incorporate this material. For stars above 260 solar masses, direct collapse to black holes might occur. The core becomes so massive that not even pair instability explosion can disrupt it. The entire star collapses into a black hole. Only gravitational waves escape. Population 3 stars likely span this entire mass range. Some explode as core collapse supernovae, some as pair instability supernovae. Some collapse directly to black holes. The variety of outcomes enriches the early universe with different element mixtures. Each explosion type leaves distinct signatures. Core collapse produces neutron stars and black holes. Pair instability produces no remnants but distinctive abundances. Direct collapse produces massive black holes immediately. These massive black holes might be the seeds for supermassive black holes found in galaxy centers today. Starting with 100 solar mass seeds and growing through accretion, they could reach millions or billions of solar masses over cosmic time. The explosion itself represents only the beginning of how these stars affected the universe. The ejector carried something more precious than energy. The Big Bang created three elements: hydrogen, 75% by mass, helium, 25%, lithium, a tiny trace. That is the complete inventory. Everything else required stars. Nuclear fusion in stellar cores assembles heavier elements. The process follows rules determined by nuclear physics. 4 hydrogen nuclei combine to make helium. 3 helium nuclei combine to make carbon. Carbon plus helium makes oxygen. The progression continues. Each fusion reaction releases energy because the final nucleus has slightly less mass than the initial nuclei. The mass difference converts to energy via Einstein's equation. This energy powers the star. It also determines which reactions can occur. Fusion up to iron releases energy. Iron sits at the peak of the binding energy curve. Nuclei lighter than iron gain stability by fusing. Nuclei heavier than iron lose stability by fusing. This makes iron the endpoint of normal stellar fusion. Creating elements heavier than iron requires different processes. Neutron capture provides the main pathway. A nucleus absorbs a neutron, becoming a heavier isotope. Sometimes the new isotope is stable. Sometimes it decays, converting the neutron to a proton and becoming a different element. 2 modes of neutron capture exist. The slow process occurs in the late stages of normal stellar evolution. The rapid process occurs in supernovae and neutron star mergers. Each produces different abundance patterns. Population. 3 stars synthesize elements through all these pathways. Hydrogen to helium in the core during main sequence. Helium to carbon and oxygen during helium burning. Carbon and oxygen to neon, magnesium, silicon during later stages. Silicon to iron in the final moments. The supernova explosion enables heavy element production. The enormous flux of neutrons during the explosion drives rapid neutron capture. Elements far beyond iron form in seconds. Gold, platinum, uranium, and all others trace their origins to these violent events. The exact abundance pattern depends on explosion energy, progenitor mass, and explosion mechanism. Different population. 3 stars produce different mixtures. A 100 solar mass star yields different abundances than a 300 solar mass star. Theoretical calculations predict the yields from population 3 supernovae. The models follow nuclear reactions in detail. They track hundreds of isotopes. They compute production rates for each element. The results show interesting patterns. Population. 3 supernovae produce much more oxygen relative to iron than modern supernovae. This happens because their cores burn more oxygen to silicon before exploding. The oxygen-rich layers get ejected completely. They also produce unusual ratios of lighter elements. Carbon to oxygen ratios differ from normal stars. Nitrogen production depends sensitively on rotation and mixing. Elements like fluorine and sodium have distinct signatures. These abundance patterns should appear in the next generation of stars. Any star forming from gas enriched by a single population 3 supernova would inherit that pattern. Astronomers search for such stars in the Milky Way halo. Several candidates have been found. Stars with metallicity below 1/1000th solar, showing unusual element ratios. Their abundances match predictions for enrichment by massive metal-free supernovae. Each discovery adds evidence for population 3 stars. The first heavy elements changed the universe fundamentally. Carbon and oxygen enabled efficient cooling. Gas clouds could now fragment into smaller clumps. Lower mass stars became possible. The initial mass function shifted downward. Silicon, magnesium, and iron provided raw materials for dust grains. Dust formation requires heavy elements. Once dust appears, it dramatically enhances cooling and shielding. Star formation efficiency increases. The transition from population 3 to population 2 star formation occurred rapidly once enrichment began. Even small amounts of metals, just 1/10,000th solar metallicity, altered the physics enough. The era of pure primordial star formation ended after perhaps 100 million years. But those first 100 million years proved crucial. Population, 3 stars created the foundation. They forged the first carbon atoms, the first oxygen molecules, the first iron nuclei. Every heavy atom in existence traces back to stellar nucleosynthesis. The elements in your body formed inside stars. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were synthesized by nuclear fusion and scattered by supernovae. The universe's first stars began that process. Their deaths seeded the cosmos. Their explosions enriched the void. Their legacy enabled everything that came after. The supernova ejecta expands at 10,000 miles per second. That velocity exceeds escape velocity from the host galaxy by wide margins. The debris will not stay confined. It spreads outward in all directions, carrying the first heavy elements ever created. Within hours, the expanding shell reaches distances of billions of miles. Within days, it crosses light weeks. Within years, light years. The material sweeps through the surrounding space, colliding with ambient gas. Each collision heats the gas and transfers momentum. The expanding shell creates a shock wave. Ahead of the shock, gas remains cold and undisturbed. Behind the shock, gas becomes hot and turbulent. The shock compresses the gas, increasing its density temporarily. This compression can actually trigger new star formation in dense regions. The shell does not expand uniformly. Instabilities develop. Rayleigh-Taylor instabilities form when heavy ejecta decelerates against lighter ambient gas. Fingers of material push outward faster. Gaps appear. The shell fragments into filaments and clumps. These clumps carry different element mixtures. Material from the core, rich in iron and silicon, forms some clumps. Material from intermediate layers, rich in oxygen and carbon, forms others. Surface layers, still mostly hydrogen and helium but lightly enriched, form additional clumps. The fragmentation means different regions receive different element doses. A gas cloud encountering an iron-rich clump gets enriched differently than one encountering an oxygen-rich clump. This creates chemical diversity even from a single supernova. After 10,000 years, the ejecta has traveled hundreds of light years. The shell now measures hundreds of light years across. Its mass, originally 30 to 200 solar masses, has mixed with perhaps 10,000 to 1 million solar masses of ambient gas. The metallicity of this mixed material reaches levels sufficient to change star formation physics. The energetics matter too. The supernova injected vast amounts of kinetic and thermal energy. This energy heats the surrounding medium to millions of degrees. Hot gas has high pressure. It expands, pushing cooler gas aside. A superbubble forms. For population 3 supernovae with energies up to 100 times normal, the superbubbles grow enormous. They can reach sizes of thousands of light years. Multiple supernovae from a cluster amplify the effect. The bubbles merge, creating supergiant shells. These shells affect the entire mini-halo. Gas gets swept up and compressed at the edges. The halo's center becomes evacuated. Subsequent star formation gets suppressed in the bubble interior. New stars form preferentially at the shell edges where gas accumulates. Some ejecta escapes the mini-halo entirely. With enough energy, material reaches escape velocity from the dark matter potential well. This material enters the intergalactic medium. It can travel vast distances before encountering another halo. Intergalactic enrichment proceeds slowly but inevitably. Each escaping supernova ejecta plume carries metals into the voids between galaxies. Over hundreds of millions of years, the enrichment spreads. The intergalactic medium's metallicity gradually rises from zero. This spreading has profound implications. It means population. 3 stars do not need to form in every halo. One massive star cluster can enrich dozens of neighboring halos. Those halos then form population, 2 stars using pre-enriched gas. The efficiency of enrichment depends on environment. In dense regions where halos cluster together, enrichment proceeds rapidly. In sparse regions with isolated halos, each must form its own population 3 stars. This creates spatial variations in when the transition from population 3 to population 2 occurs. Observations hint at these variations. Some high redshift galaxies show evidence of metal enrichment. Others at similar epochs appear more pristine. The patchiness reflects the stochastic nature of early star formation and feedback. Computer simulations attempt to capture these processes. The calculations must follow fluid dynamics, gravity, radiation transport, and chemical evolution simultaneously. The computational cost is enormous. Only the largest supercomputers can handle the problem. Results show that a single massive population 3 star can enrich a region containing 10 to 100 times its own mass in gas. A cluster of 10 such stars enriches proportionally more. The cumulative effect of many supernovae transforms entire regions. The debris also carried momentum and angular momentum. When ejecta collides with rotating gas clouds, it can spin them up or down. This affects the angular momentum of galaxies forming from those clouds. The spins of modern galaxies might partially trace back to population 3 supernova kicks. The seeding process took roughly 100 to 300 million years to substantially enrich most star-forming regions. After that, population 2 stars dominated, but the seeds planted by population 3 stars determined what came next. Their deaths provided more than just elements, though. Some left behind objects that would grow for billions of years. Not every population 3 star explodes completely. Stars above roughly 260 solar masses collapse directly without successful explosion. The core becomes so massive that no force can halt its collapse. Gravity overwhelms everything. A black hole forms. The collapse takes less than 1 second. The core, initially thousands of miles across, shrinks to an object miles in diameter. Then it crosses the event horizon, the point of no return. Light cannot escape. A black hole is born. The mass matters enormously. These are not small black holes. Core collapse from massive population. 3 stars produces black holes with masses from 30 to several hundred times our star's mass. These are intermediate mass black holes, far heavier than typical stellar black holes, but lighter than supermassive black holes. For a while, the black hole sits quietly at the center of the disrupted star. Surrounding gas, heated and blown outward by earlier fusion stages, falls back. The black hole accretes this material. Each gram of infalling matter releases tremendous energy as it spirals inward. X-rays and gamma rays pour out. This accretion phase can last thousands of years. The black hole grows as it swallows more gas. Its mass increases by perhaps 10 to 50% through fallback accretion. The exact amount depends on how much material was blown away versus how much remains bound. Eventually, the immediate surroundings clear. The black hole accreted everything nearby. Further gas lies too far away to fall in quickly. The system enters a quiet phase. The black hole becomes dormant. But the story does not end. The black hole remains embedded in the mini-halo. Gas continues cooling and settling. Some of this gas loses angular momentum through turbulence and collisions. It spirals inward. Accretion resumes, though at lower rates. The black hole also moves. It received a kick from the supernova or collapse asymmetry. This kick gives it a velocity relative to the halo center. The black hole orbits within the halo's potential, dynamically heating surrounding gas through gravitational interactions. Over millions of years, the mini-halo merges with other halos. Hierarchical structure formation proceeds. Small halos combine into larger ones. The black hole gets carried along. It sinks toward the center of the merged system through dynamical friction. When two halos merge and both contain black holes, the black holes eventually interact. They orbit each other, gradually losing energy to gravitational radiation. The orbit shrinks. The black holes spiral together. Eventually, they merge, creating a single, more massive black hole. This merging process repeats throughout cosmic history. Black holes grow by accreting gas and merging with other black holes. After billions of years, some reach millions or billions of solar masses. They become the supermassive black holes observed in galaxy centers today. Population. 3 black holes provide the seeds. Starting with 100 to 300 solar mass objects, the growth to supermassive scales requires only that accretion and mergers continue. Theoretical models show this scenario works. The timeline fits observations. Alternative scenarios exist. Direct collapse black holes, formed by catastrophic collapse of massive gas clouds, could also seed supermassive black holes. Determining which mechanism dominated requires observations. Recent detections by gravitational wave observatories provide clues. LIGO and Virgo detected mergers of black holes with masses in the 30 to 100 solar mass range. These masses exceed expectations for modern stellar black holes. They might represent descendants of population 3 stars. The gravitational wave signals carry information about the black hole's properties. Mass, spin, and even possibly the surrounding environment leave imprints. Detailed analysis of many events will eventually reveal whether population 3 remnants contribute significantly. The black holes also affect their surroundings even when not actively accreting. Their gravity influences gas dynamics. Orbiting gas feels tidal forces that can heat it. This heating can suppress further star formation in the immediate vicinity. But farther out, the black hole's gravity helps hold the system together. It contributes to the total mass, deepening the potential well. More gas can be retained. The system can grow more massive. This positive feedback accelerates galaxy formation. Some population. 3 black holes might have been ejected from their host halos. Strong gravitational interactions during mergers can produce kicks exceeding escape velocity. These orphan black holes wander through the intergalactic medium, occasionally encountering and accreting gas clouds. The ultimate fate of all these black holes remains uncertain. Do they eventually merge into the central supermassive black hole? Do some remain in the halo as a population of intermediate mass black holes? Observations have not yet answered definitively. What we know for certain: population, 3 stars created the first stellar mass black holes. Those black holes seeded later growth. They contributed to the diverse population of black holes observed today. Their siblings that did explode left a different kind of legacy. The second generation forms from enriched gas, not pure hydrogen and helium anymore. Now the mix includes carbon, oxygen, nitrogen, silicon, iron. The metallicity remains low by modern standards, perhaps 1/1000th to 1/10th our star's metallicity. But compared to 0, it changes everything. Carbon and oxygen are the game changers. These elements have electronic structures that allow efficient radiative cooling. Collisions excite electrons into higher energy states. De-excitation releases photons. Each photon carries away energy, cooling the gas. The cooling rate increases dramatically. Gas that previously required millions of years to cool now cools in hundreds of thousands of years. Temperatures drop lower, reaching 100 to 500 degrees instead of thousands. Pressure support weakens. Fragmentation becomes possible. Instead of 1 or 2 massive stars forming per halo, dozens or hundreds of stars form. The mass spectrum broadens. Stars with masses like our own, or even smaller, can now form. The initial mass function shifts from top-heavy to something resembling the modern distribution. These population 2 stars behave more like stars we see today. They fuse hydrogen steadily. They evolve through well-understood phases. Their lifetimes extend. Low mass population. 2 stars formed in the early universe still shine today. 13 billion years later. The chemical composition affects internal structure. With more metals comes higher opacity. Radiation gets trapped more easily in the stellar interior. This affects energy transport. Convection zones develop differently. Mixing patterns change. Surface temperatures run cooler than population. 3 stars at equivalent mass, a 50 solar mass. Population 2 star might have a surface temperature of 40,000 degrees instead of 90,000. Still hot, still blue, but less extreme. The radiation spectrum peaks at longer wavelengths. This cooler temperature means less efficient ionization of surrounding gas. Population 2 stars require more total numbers to reionize the same volume, but their longer lifetimes compensate. They maintain ionization over millions of years instead of just a few million. The first population 2 stars formed within 10 to 30 million years after the first population 3 supernovae. The time depends on how long gas needed to cool and recollapse after being disrupted by explosions. Different regions transitioned at different times. Some halos experienced immediate transition. A population 3 supernova enriched the gas. Star formation resumed quickly using that enriched material. Population 2 stars formed alongside late-forming population 3 stars. Other halos took longer. The supernova feedback expelled gas from the halo. The gas had to fall back in. This delayed star formation by 100 million years or more. When stars finally formed, the metallicity might have increased further through mixing with ejecta from other halos. The diversity of enrichment histories created diversity in population 2 stars. Some formed from gas, enriched by a single supernova, showing that supernova's particular abundance pattern. Others formed from well-mixed gas, affected by multiple supernovae, showing averaged abundances. Astronomers observed this diversity in ancient metal-poor stars. Each star's spectrum reveals a unique chemical fingerprint. By analyzing many stars, researchers reconstruct the early enrichment history. They identify which abundance patterns came from which types of supernovae. Some patterns clearly point to pair instability supernovae. Others indicate core collapse from moderately massive stars. A few show evidence of enrichment by extremely energetic hypernovae. Each pattern teaches us about population 3 stars that died to create that enrichment. Population 2 stars also contributed to further enrichment. Their supernovae added more heavy elements. The metallicity ratcheted upward with each generation. After several 100 million years, the average metallicity reached levels where population 1 stars, like our own, could form. The transition from population 2 to population 1 remains gradual and ongoing. The Milky Way's halo contains ancient population 2 stars. The disk contains younger population 1 stars. The distinction blurs at intermediate ages and metallicities. What matters is the inheritance. Population 2 stars exist because population 3 stars died. The enrichment made them possible. The diversity arose from the variety of population 3 supernovae. The entire cosmic chemical evolution traces back to that first generation. Without population 3 deaths, population 2 life would not exist. Without population 2 evolution, population 1 stars like ours could not form. Without our star, Earth would not exist. The chain of causation runs straight through stellar nucleosynthesis. Some of that enriched material ended up very close to home. Our galaxy contains ghosts. Stars so old they formed when the universe was less than 1 billion years old. So metal-poor their atmospheres preserve nearly primordial composition. So faint they hide among billions of younger stars. Astronomers hunt them in the Milky Way's halo. The halo surrounds the disk in a roughly spherical distribution. It contains globular clusters, ancient stellar streams, and individual field stars. These objects orbit the galaxy's center on elongated paths, plunging through the disk and soaring back out. Many halo stars show extreme metal deficiency. Spectroscopy reveals iron abundances 10,000 times lower than our star. These are among the oldest stars in the galaxy. They formed from gas only lightly enriched by the very first supernovae. Each ultra-metal poor star represents a fossil record. Its atmosphere preserves the chemical composition of the gas from which it formed. That gas was enriched by one or a few population 3 supernovae. By reading the star's spectrum, astronomers reconstruct what happened billions of years ago. Certain stars show bizarre abundance patterns, inconsistent with normal enrichment. One star might have high carbon but low iron. Another might show enhanced oxygen relative to magnesium. These oddities point to enrichment by unusual supernovae. One particular star, catalogued as HE 1000, 327 to 2000, 326, shows remarkable properties. Its iron abundance reaches only 1/250,000th of our stars. But carbon appears relatively abundant. The pattern suggests enrichment by a faint population. 3 supernova that ejected its outer layers but left much of the iron core behind. Another star, SMSS J031300, has even lower iron abundance. Astronomers initially measured iron below detection limits. The iron-to-hydrogen ratio is at least 50,000 times lower than our stars. Yet calcium and magnesium appear in measurable amounts. This pattern implies enrichment by an extremely energetic explosion that ejected lighter elements efficiently but produced little iron. These stars likely formed in small halos that later merged into the Milky Way. The merging process scattered them throughout the halo. Each orbit carries stories from different environments in the early universe. By analyzing hundreds of ultra-metal poor stars, researchers build a statistical picture. They determine how common different abundance patterns are. They infer what population, 3 mass distribution, and supernova energies must have been. Results suggest population. 3 stars had masses ranging from 10 to several hundred solar masses. The lower mass stars produced core collapse supernovae with normal energies. Higher mass stars produced pair instability supernovae or hypernovae. The diversity of outcomes created the diversity of abundance patterns. The spatial distribution matters too. Ultra-metal poor stars concentrate somewhat toward the inner halo. This suggests early star formation occurred preferentially in denser regions that eventually formed the galactic center. Outer halo stars show slightly different abundance patterns, hinting at different enrichment histories. Some globular clusters contain stars with unusual abundances. The cluster could have formed from gas enriched by population 3 supernovae. If multiple supernovae enrich the same gas cloud before star formation, the resulting cluster preserves a record of several population 3 events. Not all ancient stars are ultrametal poor. Some halos experienced rapid enrichment. Multiple generations of stars formed in quick succession. By the time the stars astronomers observed formed, the metallicity had risen to 1% solar or higher. These stars tell us nothing about population 3 stars directly. The search continues. Large spectroscopic surveys observe millions of stars. Automated algorithms flag candidates with unusual spectra. Follow-up observations confirm the most interesting targets. Each new discovery adds one more data point. Future surveys will find fainter and more distant halo stars. The outer reaches of the Milky Way remain poorly explored. Undiscovered populations of ancient stars likely exist in the distant halo and in satellite galaxies. The chemical abundance patterns also appear in other galaxies. Observations of ultra-faint dwarf galaxies show low metallicity stars with unusual abundances. These galaxies formed in the early universe and experienced minimal star formation since they preserve population 3 enrichment signatures. Theoretical chemodynamic models attempt to connect observations to population 3 properties. The models simulate the Milky Way's formation and early chemical evolution. They predict what we should observe if population 3 stars had certain mass distributions and explosion properties. Comparing models to observations constrains population 3 star formation. The data favor models with typical masses around 50 to 100 solar masses. Models with very different mass distributions fail to reproduce observed abundance patterns. The Milky Way's oldest stars are not mere curiosities, they are laboratories. Each one tests theories of population, 3 stars, and early nucleosynthesis. Each abundance measurement constrains models. Each discovery reveals another piece of cosmic history. Those ancient photons, captured in old stellar atmospheres, carry a profound message about our origins. A universe of pure hydrogen and helium is sterile. No rocky planets can form without silicon, magnesium, iron. No water can exist without oxygen. No organic molecules without carbon. No life without nitrogen and phosphorus. Everything complex requires heavy elements. The Big Bang could not produce heavy elements. Nuclear physics forbids it. The reactions that form elements heavier than lithium require conditions that did not exist in the expanding early universe. Stars provide the only pathway, but stars need time to form. The first stars took 200 million years to ignite. During that time, the universe contained only hydrogen and helium. When population 3 stars finally formed, they merely concentrated those elements. No new chemistry emerged. The critical moment came when the first star died. The supernova explosion processed stellar material through extreme temperatures and densities. Fusion reactions that require millions of degrees and nuclear matter density proceeded for the first time. Heavy elements formed. The explosion dispersed those elements. Without dispersion, the heavy elements would remain locked in a compact remnant. Dispersion spread them through hundreds to thousands of light years. Gas clouds light years away encountered this enriched material. Star formation from mixed gas became possible. The paradox is clear. Population 3 stars had to die for anything interesting to happen afterward. Their deaths were not tragic endings. They were necessary beginnings. Destruction enabled creation. Consider the alternative. What if population 3 stars never exploded? What if they all collapsed quietly into black holes, taking their heavy elements with them? The universe would remain pure hydrogen and helium forever. No enrichment, no population, 2 stars, no galaxies as we know them, just primordial gas and black holes. Or imagine if population 3 stars lived longer, if they burned steadily for billions of years like lower mass stars. Enrichment would be delayed billions of years. The entire timeline of cosmic evolution shifts. Galaxies forming today would still be primordial. No heavy elements anywhere. The short lifetimes proved essential. Rapid death meant rapid enrichment. Within tens of millions of years of the first star forming, heavy elements spread through significant volumes. The transition to population 2 stars occurred quickly. Chemical evolution accelerated. The explosion violence mattered too. Gentle mass loss through stellar winds would enrich only the immediate surroundings. The gas would remain marginally bound to the halo. Much would fall back. Strong explosions ejected gas at high velocities. Escape from the halo, spread into the intergalactic medium, wide distribution. The energy injection also played a role. Supernovae heated gas to millions of degrees. Hot gas expands and mixes efficiently. Turbulence stirs heavy elements into surrounding material. Without this heating and mixing, enrichment would proceed in isolated pockets. Uniform enrichment requires violent feedback. Even the supernova remnants contributed. Black holes from population 3 stars became seeds for supermassive black holes. Those supermassive black holes power quasars and active galactic nuclei. The energy output from accreting black holes affects galaxy evolution over billions of years. The death also limited further population 3 formation. Supernova feedback heated and expelled gas from mini-halos. This suppressed subsequent star formation in those halos. It prevented runaway formation of more massive stars. The transition to population 2 occurred naturally through self-regulation. Theoretical models confirm this sequence. Simulations that include population 3 stars and their feedback produce galaxies resembling observations. Simulations without proper population 3 physics fail. The early chemical enrichment proves crucial for later galaxy formation. The philosophical implication resonates. Progress requires change. Change requires destruction. The old must pass for the new to emerge. Population. 3 stars had to die for the universe to become interesting. This principle applies beyond astronomy. Biological evolution proceeds through death. Ecosystems recycle nutrients from dead organisms. Cultures evolve as old ideas fade and new ones emerge. The pattern repeats across scales. For the universe, population, 3 deaths represented the first creative destruction. Their explosions transformed the cosmos from simple to complex, from uniform to diverse, from sterile to potentially life-bearing. We owe our existence to their deaths. Every atom heavier than helium in your body came from stellar nucleosynthesis. Much of it traces back to those first generations. The calcium in your bones was forged in ancient supernovae. The iron in your blood was synthesized by massive stars billions of years ago. The connection runs deeper than just providing raw materials, though. Without heavy elements, chemistry becomes trivial. With them, the combinatorial possibilities explode. Carbon has 4 valence electrons. This allows it to form 4 covalent bonds simultaneously. Carbon atoms can bond to each other, creating chains and rings. They can bond to hydrogen, oxygen, nitrogen, forming functional groups. The number of possible carbon-based molecules reaches astronomical values. Without carbon, complex chemistry does not exist. Hydrogen and helium form exactly 2 stable molecules. Molecular hydrogen, ionized helium hydride. That is everything. No diversity, no complexity, no possibility of life. Population. 3 supernovae created the first carbon atoms. 3 helium nuclei fused in stellar cores, producing carbon-12. Some carbon-13 formed through side reactions. The supernova explosion ejected this carbon into space. The clock on complex chemistry started ticking. Oxygen came from helium and carbon fusion. Carbon plus helium produces oxygen-16. Additional reactions created oxygen-17 and 18. Oxygen has 6 valence electrons. It forms 2 covalent bonds readily. Combined with carbon and hydrogen, it enables aldehydes, ketones, alcohols, carboxylic acids. Thousands of organic compounds become possible. Nitrogen formed through somewhat different pathways. The CNO cycle in stellar hydrogen burning produces nitrogen-14. Some got ejected by stellar winds. More got released in supernovae. Nitrogen has 5 valence electrons. Combined with carbon, hydrogen, and oxygen, it creates amino acids. Amino acids polymerize into proteins. Proteins enable biological function. Phosphorus required heavier elements. Silicon burning produces phosphorus through nuclear reactions. Supernovae ejected phosphorus into space. Phosphorus has 5 valence electrons and forms compounds with oxygen that are crucial for energy transfer. ATP, the universal energy currency of life, contains phosphorus. Sulfur came from oxygen and silicon burning. Its chemistry resembles oxygen, but with different bond strengths and reactivities. Some amino acids contain sulfur. Important biomolecules like coenzyme A incorporate sulfur. Iron emerged from silicon burning and neutron capture. Though not a primary component of organic molecules, iron plays crucial roles in biochemistry. Hemoglobin uses iron to bind oxygen. Many enzymes require iron cofactors. Electron transport chains involve iron-sulfur clusters. Population. 3 supernovae provided all these elements. The first generation synthesized and distributed the complete set of biologically essential elements, not in abundance, not in ideal ratios, but present, available for incorporation into later chemistry. Gas enriched by population. 3 supernovae had metallicities around 1/millionth to 1,000th solar, tiny amounts by modern standards, yet sufficient to enable complex molecules that were previously impossible. When population 2 stars formed from this enriched gas, they concentrated the heavy elements further, planets forming around population. 2 stars inherited these elements. Rocky planets became possible. Atmospheres containing oxygen and nitrogen developed. Liquid water condensed. The timeline matters. By 1 billion years after the Big Bang, significant enrichment had occurred. Metallicity in star-forming regions reached perhaps 1% solar, enough for Earth-like planets to form. Life remains unlikely on such planets because they orbit metal-poor stars with unusual properties. But the basic ingredients existed. By 3 billion years after the Big Bang, metallicity in many regions reached 10% solar or higher. Stars like our own started forming. Planets with compositions similar to Earth became common. The probability of life-bearing worlds increased dramatically. Our Earth formed 9 billion years after the Big Bang. The gas from which our star and planets condensed contained metals from thousands of previous stellar generations. The iron core, the silicon mantle, the oxygen atmosphere, the carbon in all living things, all trace back through those generations to the first supernovae. The path from population 3 supernovae to biology required billions of years. Gas enrichment, star formation, planet formation, prebiotic chemistry, the emergence of self-replication, evolution. Each step took time, but each step was enabled by the heavy elements created and distributed by dying stars. The specific abundance patterns matter too. Life on Earth uses carbon-based chemistry. This works because carbon was abundant relative to other heavy elements in the gas forming our star. If silicon had dominated instead, chemistry would be different. Perhaps life could still emerge, but it would operate differently. The ratio of nitrogen to carbon affects atmospheric chemistry. Too much nitrogen, and you get dense, choking atmospheres. Too little, and amino acid synthesis becomes difficult. Earth's ratio happens to be favorable. This ratio ultimately traces back to nuclear reaction rates in massive stars. Phosphorus scarcity compared to other essential elements might limit life's abundance in the universe. Supernovae produce less phosphorus relative to carbon, oxygen, and nitrogen. Planets might contain insufficient phosphorus for life as we know it. This would make life rare, even where other conditions favor it. These details remain speculative. We know of only one example of life, Earth's biosphere. Generalizing from one data point is risky, but the connection between stellar nucleosynthesis and biology is undeniable. Population. 3 stars did not create life, but they created the necessary ingredients. Without their deaths distributing heavy elements, life would be impossible. The chain of causation runs unbroken from the first supernovae to living cells on Earth. Yet, discovering this chain required technology beyond imagination just decades ago. Theoretical predictions for population 3 stars existed since the 1970s. Researchers calculated their masses, temperatures, lifetimes, and spectra. The models grew increasingly sophisticated. Computer simulations tracked their formation and evolution. By 2000, scientists had detailed predictions about what these stars should look like. Finding them seemed impossible. They existed over 13 billion years ago. Their light had traveled across the entire observable universe. Redshift stretched ultraviolet emission into infrared. The brightness dimmed by factors of millions due to distance. Even the largest telescopes could barely detect distant galaxies, let alone individual stars. Hubble Space Telescope pushed boundaries. It observed galaxies at redshifts beyond 6. It captured light from when the universe was less than 1 billion years old. But Hubble's infrared capabilities were limited. Its mirror, 2.4 meters across, lacked the collecting area for faint, distant objects. Attempts to detect population 3 stars using Hubble failed. Researchers observed candidate galaxies. They analyzed spectra, searching for signatures of extremely hot stars. Some claimed tentative detections. Peer review found alternative explanations. The evidence never reached convincing levels. The James Webb Space Telescope changed everything. Its mirror spans 6.5 meters. That is 7 times more collecting area than Hubble. The sensitivity to infrared light exceeds Hubble by factors of 10 to 100. depending on wavelength. Webb launched in December 2021. After 6 months of deployment and calibration, science operations began. Astronomers submitted proposals for observing time. The competition was fierce. Only the best science programs received time. One approved program targeted gravitationally lensed fields behind massive galaxy clusters. The strategy was simple. Use the cluster's gravity to magnify distant galaxies. Use Webb's sensitivity to capture their faint light. Use spectroscopy to analyze their properties. The program selected 6 cluster fields, including MaxJ 416. Deep exposures accumulated dozens of hours. The observations targeted specific regions where lensing models predicted high magnification. Data flowed to archives. Researchers worldwide accessed the observations. Multiple teams began independent analyses. Each team developed their own processing pipelines and analysis techniques. One team focused on searching for helium-2 emission. This spectral line requires the hottest stars. If population 3 stars exist anywhere, they should produce strong helium-2. The search targeted hundreds of lensed galaxies. Most galaxies showed no helium-2 emission. Their spectra indicated normal stellar populations enriched with metals. Then the team examined LAP-1b. The spectrum showed clear helium-2 emission. The signal-to-noise ratio exceeded 5. Definitely real. Further analysis checked for alternative explanations. Could active galactic nucleus produce the signal? The emission line ratios ruled that out. Could shock heating explain it? Again, the ratios disagreed. The only consistent explanation: extremely hot, massive metal-poor stars. Confirmation required checking the 3 theoretical criteria. Metallicity measurements from absorption lines showed near-zero heavy elements. The galaxy's mass and size matched predictions for mini-halos. The emission properties suggested very few extremely luminous stars rather than a normal stellar population. All criteria satisfied. The team prepared a manuscript. They documented every step of the analysis. They addressed potential alternative explanations systematically. They calculated statistical significance. The confidence level exceeded 5 sigma. The paper underwent peer review. Expert referees scrutinized the data reduction, analysis methods, and conclusions. They requested additional tests. The team provided them. After revisions, the paper was accepted for publication in astrophysical journal letters. The detection succeeded because multiple factors aligned. Webb's unprecedented sensitivity, gravitational lensing, providing 100-fold magnification, LAP-1b happening to exist in the right place at the right time, the careful search strategy, the rigorous analysis. Remove any one factor and the detection fails. Without Webb, insufficient photons. Without lensing, too faint. Without careful target selection, wrong galaxies observed. Without rigorous analysis, signal missed or misinterpreted. The achievement represents a triumph of planning and execution. Decades of preparation designing Webb, years developing lensing models for cluster fields, months of observation and data reduction, weeks of intensive analysis, all converging to capture photons from stars that formed 13 billion years ago. The detection opens a new observational window. We now know population 3 stars exist. We know what signatures to search for. We know which environments to target. The search will continue and expand. But the implications extend beyond confirming an old prediction. This discovery forces us to rethink what we thought we knew. Galaxy formation models predicted a gradual build-up. Small halos merge into larger ones. Star formation proceeds slowly. Metallicity increases steadily over time. Galaxies grow from dwarfs to giants over billions of years. LAP-1b challenges this picture. At redshift 6.6, just 800 million years after the Big Bang, it already shows active star formation. Population: 3 stars are present, suggesting this might be among the first or second generation of stars in this halo. The timeline is compressed. If population 3 stars still exist at this epoch, what does that say about enrichment timescales? Previous models assumed enrichment would occur rapidly once started. A few supernovae should raise metallicity enough to transition to population 2, yet LAP-1b maintains near-zero metallicity, despite being hundreds of millions of years old. Two possibilities emerge. Either LAP-1b formed in an extremely isolated region that avoided prior enrichment, or the enrichment process proceeds more slowly than models predicted. Both options require rethinking standard scenarios. The isolated formation scenario suggests the early universe had more spatial variation than expected. Some regions enriched quickly through clustered star formation. Other regions remained pristine much longer due to isolation. This patchiness would affect reionization. Ionized bubbles would grow unevenly. The slow enrichment scenario suggests feedback might be more effective at delaying subsequent star formation. One population 3 supernova explodes. Gas gets expelled from the halo. Before the gas falls back and forms new stars, hundreds of millions of years pass. By then, the halo has grown through mergers. New star formation pulls in fresh, unenriched gas from the intergalactic medium. Either way, the discovery indicates our timeline might be wrong. Population 3 stars might have contributed to reionization more than previously thought. If they existed in significant numbers at redshift 6 to 7, their ionizing photons would have major impact. Reionization constraints become tighter. We know the universe was mostly ionized by redshift 6. We observe that LAP-1b contains population 3 stars at redshift 6.6. The transition must occur rapidly between these redshifts. This compressed timeline requires higher efficiency of ionizing photon production. The discovery also affects supermassive black hole formation theories. If population 3 stars exist at late times, their remnant black holes also form late. These late-forming black holes have less time to grow through accretion. Reaching billions of solar masses by redshift 6 becomes harder. Alternative black hole formation channels must contribute more. Direct collapsed black holes, formed without stars, might be necessary to explain early quasars, or black hole accretion rates must exceed expectations. The constraints tighten. Cosmological simulations require updates. Current simulations implement simplified population, 3 prescriptions, a brief initial burst followed by rapid transition to population 2. The LAP-1b observation suggests this oversimplifies reality. Some regions should maintain population 3 formation much longer. Updated simulations will explore spatially inhomogeneous enrichment. They will track individual halos more carefully. They will implement more realistic feedback that can delay subsequent star formation. The computational cost will increase, but so will the realism. Chemical evolution models also need revision. The abundance patterns observed in ultrametal poor stars show diversity. Some patterns indicate enrichment by single supernovae. Others show mixed signatures. If population 3 formation extends over longer times and in more places than expected, this diversity becomes easier to explain. The initial mass function of population 3 stars remains debated. Do they form with typical masses around 50 solar masses or several hundred? LAP-1b's properties favor the lower mass end. The emission signatures match stars around 100 to 200 solar masses better than higher mass objects. This constrains formation physics. Dust formation in the early universe connects to population 3 star properties. Their supernovae create the first heavy elements. But dust requires specific conditions to condense. Temperature, density, and composition must be right. If population 3 stars exist at late times, dust formation timing needs reassessment. The cosmic infrared background, faint light filling space at infrared wavelengths, receives contributions from early galaxies. Models of this background depend on when stars formed and what types. Adding extended population 3 contribution changes predictions. Future observations can test this. First light, the moment the universe's first stars ignited, might occur earlier than thought. If population 3 stars can survive to redshift 6.6, perhaps they formed at redshift 20 or 30, rather than 15 to 20. Pushing first light earlier affects many related phenomena. Every aspect of early universe cosmology connects to population. 3 stars somehow. They dominate the first few 100 million years. Their feedback shapes structure formation. Their remnants seed later growth. Their nucleosynthesis enables chemistry. Getting their properties right is essential for understanding cosmic dawn. LAP-1b provides our first solid data point. One detection does not solve all problems, but it anchors theories to reality. Models must explain LAP-1b's existence and properties. Those that cannot are ruled out. Science progresses through confrontation with data. The search will not stop here. LAP-1b is not unique. Statistical arguments suggest thousands of similar objects exist within Webb's observable volume. The challenge is finding them. Most lack the perfect gravitational lensing alignment needed to boost their brightness. Current surveys scan large areas of sky to moderate depth. They detect thousands of high redshift galaxies. Spectroscopic follow-up targets the brightest candidates. Most show normal enriched stellar populations. Occasional objects show unusual properties worth detailed study. Deep surveys focus on small areas, observing for hundreds of hours. They detect fainter objects. The probability of finding extremely rare populations increases. Programs targeting lensed cluster fields optimize for faint magnified sources. Multiple cluster fields are being observed. MaxJ 416 is one of 6 from the Hubble frontier fields. Webb is observing all 6 with various programs. Each field provides opportunities to find magnified high redshift galaxies. More LAP-1b-like objects should emerge from these data. Beyond frontier fields, Webb observes other lensing clusters. The PEARLS program targets multiple clusters. The GLASS program focuses on deep spectroscopy. The UN COVA program maps ultra-deep fields. Each program has different goals, but all contribute to finding rare objects. Machine learning algorithms aid the search. Trained on known galaxy spectra, algorithms can flag unusual candidates automatically. Human experts then examine flagged objects carefully. This combination of automation and expertise accelerates discovery. The spectroscopic confirmation requires significant telescope time. Each object needs hours of exposure to obtain signal-to-noise sufficient for analysis. Webb can observe only so many objects per year. Prioritization becomes critical. Which candidates deserve expensive follow-up? Photometry provides initial screening. Multiband imaging constrains redshift and basic properties. Objects showing very blue colors but faint apparent magnitudes might be distant young galaxies. Objects with unusual color combinations might indicate atypical stellar populations. Strong emission lines boost observability. Lyman alpha emission from high redshift galaxies can be detected in imaging. Objects showing strong Lyman alpha are good spectroscopy candidates. If helium-2 emission is as strong as models predict, it too might appear in narrowband imaging. Coordinated multi-wavelength observations enhance discovery potential. Webb provides infrared data. Hubble adds optical context. Chandra X-ray Observatory checks for active galactic nuclei. ALMA radio telescope measures molecular gas. Each wavelength contributes unique information. Serendipitous discoveries matter too. Astronomers examining data for one purpose notice unexpected features. A strange spectrum in the background of a target galaxy, an unusual color in a survey image. Many major discoveries began as serendipitous finds. Future facilities will advance the search. The Nancy Grace Roman Space Telescope will launch in the late 2020s. Its wide field of view will survey huge areas. Though less sensitive than Webb, the large volume compensated. Roman should find hundreds of high redshift galaxy candidates. Extremely Large Telescope, a ground-based 30-meter telescope, will provide unprecedented spectroscopic capabilities. Its collecting area dwarfs Webb. It can obtain spectra of fainter objects faster. The combination of Webb for infrared detection and ELT for spectroscopic follow-up will be powerful. gravitational wave observatories might contribute indirectly. If population 3 remnant black holes merge, their gravitational waves encode the black hole masses. Detecting multiple mergers in the early universe would constrain how many population 3 stars formed. This complements direct optical observations. Theoretical predictions guide the search. Simulations predict where population 3 galaxies should appear in observable space. What range of brightnesses and sizes to expect? What fraction should show detectable signatures? Observers use these predictions to optimize search strategies. The ultimate goal extends beyond counting population 3 galaxies. Understanding their properties and evolution reveals early universe physics. How did the first stars form? What determined their masses? How did they affect their surroundings? When did the transition to metal-enriched star formation occur? Each new detection adds information. Eventually, a census of population 3 galaxies will emerge. We will know their abundance at different epochs. We will understand their typical properties and the range of variation. We will trace their evolution as the universe aged. This census will test theoretical models decisively. Models predict specific numbers and properties. Observations will confirm or refute those predictions. Discrepancies will drive model improvements. The cycle of prediction and observation advances understanding. The search also has philosophical dimension. Finding the first stars connects us to cosmic origins. These objects represent the beginning of complexity, the first step from simple to complex, from uniform to diverse, from hydrogen to heavy elements. They are our ancestors in a real sense, not biological ancestors, chemical ancestors. The atoms in our bodies passed through many stars, but the chain began with population 3 stars. They created the first heavy atoms. Everything else followed. Webb has given us the first glimpse. LAP-1b shines across 13 billion light-years as proof. The first stars did exist. They looked like theory predicted. We can find them and study them. The cosmic dawn has begun revealing its secrets. The search continues. More discoveries await. Each detection brings us closer to understanding the moment darkness ended and light filled the universe for the first time. After 13.8 billion years, we finally see the beginning.